Good afternoon, everyone. I'm Sanjeev Bhatia. Uh, I won't talk much about policies. I will try to cover some of the technical aspects on the energy storage. We all are talking about, I know, like even in these sessions on renewable, on the EV charging, but we need to look into which is one of the most important challenges that from the infrastructure perspective, from the generation or from the decarbonization perspective, what's the role of the energy storage and why this plays a very significant role. As we all are well aware about the targets, I really don't know. As on today looks quite optimistic targets to get some sort of net zero by 2040. The pace in which ultimate infrastructure is coming up on the power system side. If you look into the power system, primarily like contribute around 30 to 40% of the overall emission. So as we all are aware about, to meet these particular targets, renewable generation, primarily solar and wind, I'll say, are coming up at the big pace in all the countries. Even if we talk about India, Europe, China, US, each and every country is putting renewable generation to the big extent. And this includes solar and wind to the large scale. Based on the countries, if you look into US, these are primarily coming out with a solar type of generation. If you look into Australia, primarily the wind dominating type of generation. So if we look into what's the challenges we are talking about when only the renewable generation will come up, like in the combination of the existing combined cycle, conventional generation, solid fuel generations. Primarily we are talking about, we are adding solar. So obviously somewhere we are not able to achieve the same reliability and stability of the power system. The whole reason is, as we know, that as we are adding more and more solar and more wind, primarily these are the generations which are too much dependent on the natural factors, right? Solar would depend upon the solar irradiance, the wind will depend upon the wind blow. So obviously during the day, during the time of the day, during the season of in the air, primarily the generation would be the intermittent type of. So obviously we need to look into that, how reliable these generations are, and with respect to the stability when we are connecting these renewable generation to the grid. Other aspect, very important aspect, we talk about power supply and demand imbalance. As I already covered that when we talk about that these are intermittent in generation. So obviously during the day, like solar generation would be at the peak based on the solar irradiance, but in between if there is a cloud coverage, obviously due to the irradiance, generation will go down and combined cycle will pick up. And we know that existing conventional combined cycle, or even if we add it, some sort of like simple cycle aeroderivative type of machines which people started using it, these have their own ramp rates of 10 minutes to 15 minutes, even the small aeroderivative type of machines. So obviously like power supply and demand is going to be the big challenge. Changes in the transmission flow patterns. As we are adding more and more renewable in the existing grid, there are the challenges. Like there are the challenges in the sense of like whether our transmission system is good enough to manage when generation is at peak from the solar or the wind, and when generation is going down and combined cycle is picking up. How these congestions from the stability perspective can be taken care of when the more and more renewable generation is coming up. Why I'm bringing the stability again and again, there are very two important technical terms which are impacted. One is the voltage stability and second is the frequency stability. Because these are the static systems, right? They are not having any inertia. They don't have any rotational equipment which can help in terms of the frequency regulation or maintaining the voltage stability. We might have like seen very recently some sort of blackouts in Spain. All these were primarily on account of the voltage instability and frequency regulation if we go into the root cause analysis of those incidents. In US, couple of years before, Texas in the peak winter completely went down for a couple of days. And we can imagine with the temperature of minus 25 degrees, when the complete generation went down, complete blackout, what could be the situation? This is one of the reasons in US, where at present the 40% of the demand is being met by the solar generation along with the combined cycle generation. There are a lot of incidents happening in California. Even California is having the hybrid generation with the energy storage systems. Grid infrastructure, I already touched base. System inertia, I've already touched base, which we people are pretty clear that how the system inertia is being impacted when we are talking about adding more and more renewable. So what's the solution? Means I won't say that like power project developers, utilities, even like we talk about government sectors or private sectors, they are not thinking about that what's the solution. So obviously the solution which is coming out is the energy storage, hybrid generation, energy storage solutions. There are different technologies of the energy storage which are already matured or which are coming up in the nascent stage as well. So when we talk about energy storage, obviously we talk about two things, right? Short duration energy storage, long duration energy storage. When we talk about the big utility scale type of power sector, obviously in general we talk about the long duration energy storage. Why I'll cover that in the next couple of slides, that why the long duration energy storage is quite important when we talk about the large utility scale generation structure. So if means we all know that energy, what is energy storage? This can be any technology, right? This can be the mechanical type of battery energy storage system, as we have already covered, like long duration battery energy storage systems, pumped hydro type of, lot of new technologies. I'm not telling pumped hydro is a new technology, but a lot of new technology like gravity based energy storage, compressed air energy storage, all these technologies are evolving. There are technologies which are even at the very, very early stage and the pilot stage type of things. So if you look into primarily, like if we divide the long duration energy storage technology, we can just divide it into the four. One is mechanical, chemical, electrochemical, and thermal. When we talk about to start from chemical, this is primarily like power to gas to power type of technology. When I say power to gas, primarily like the energy converts into the hydrogen, and then hydrogen is stored, and then in turn hydrogen is either used to run the hydrogen based turbines or even in the fuel cells type of thing. Nowadays, like fuel cells are coming up in the big way. Just to take as an example, if we look into, I can take as an example of US, because primarily we people are working in the US. As we all know that data centers are coming up in the big way, and more or less all the big data centers are coming with the captive power generations. And when we say data center, like at present we are working for one of the data center in US, which is for Chevron. This is 2.5 gigawatt data center and completely off grid. And we all know that what's the reliability we needed for the data center from the power generation perspective. So this primarily includes obviously the combined cycle generation. When I say combined cycle generation, is the gas-based generation with the steam turbines, with the fuel cells, with the battery energy storage system, and the small aeroderivative machines of the 15 to 20 megawatt type of. So means why I'm bringing that point, fuel cells are now coming up in the big way, primarily in the captive generation for the data center type of requirements. Electrochemical means, we all know electrochemical, primarily this includes all the battery energy storage systems, whatever we are talking about. The most matured battery energy storage system at present on the industrial level on the big scale is the lithium ion batteries. These are quite matured in the sense of, if you look into 80 to 90% of the electrochemical, I won't say 80 to 90, 94 to 96% of the electrochemical installations are primarily based on the lithium ion technology. Obviously, like there are other technologies which are evolving, which are at the research stage, primarily the flow type of batteries and all these. Mechanical primarily, if you ask to me, like pumped hydro comes into the mechanical, which is obviously considered as the most matured technology from the energy storage perspective. At around 90% of the long duration energy storage installations are the pump hydro as of now. Other technologies like which are coming up are like at the very early stages, compressed air energy storage. This is also one of the mechanical type of technology. In compressed air energy storage, primarily the compressed energy is stored, and that compressed energy is used to drive the engines. And compressed air is also stored in the form of the thermal energy in form of adiabatic, and when the discharge happens, this provides the heat ultimately. Other technologies which are coming up, I already touched base very briefly, the gravity-based technology, where primarily the heavy loads are left and energy is stored, and when the energy is required, they just drop it down to get the energy conversion, potential energy to the electrical energy type of things. If we just compare between the different technologies, if we look into mechanical, like pumped hydro is at the commercial stage. There, this primarily talks about that what's the backup duration from the energy. When I say backup duration, that is very important term from the energy storage, because energy is stored and energy will be used when this is discharged per se. Say for an example, if we talk about battery energy storage systems, even the big batteries, like just to take as an example, like California, we already talked about. California is one of the state in US or even at the global level which have the maximum hybrid generation. When I am using the hybrid generation term, means at the utility scale, a lot of plans are coming up nowadays with the solar and battery energy storage system type of hybrid generation concept. And why, I'll just try to cover it very quickly in the next slide. So California is a state which has I'll say in terms of volume, in terms of capacity, or in terms of duration, the maximum number of battery energy storage system. And duration is very important. Like if I say 200 megawatt of the BESS, is it for 2 hours or 4 hours? Like this means that for how much duration this can discharge and this can provide the required power output. So this is the slide which primarily talks about all the technologies, like at which stage these are pilot stage or these are at the R&D stage, and what's the normally like in terms of the megawatt ratings and the backup discharge duration we are getting it from these technologies. This is a very important slide if you look into, like, which we already, I think in the last session also I was hearing that particular thing. So if you look into this particular I'll say the bar chart or graph per se, this is like very famous, the terminology which is being used like is the duck curve. When I say duck curve, this primarily the term evolved from the CASO. CASO is the California authority, like as like in India we have power grid. So there the state-based authorities are there. So if you look into that particular curve, and if you look into during the day, like when the solar irradiance at its peak, then primarily our fossil generation is going down, and fossil generation is going down. This means that obviously, like if the plant is with the BESS, then obviously like at that time the import tariffs for charging the BESS are very low. So this particular power is being used to charge the BESS. And when, like if you look into the morning time or the evening time when the solar irradiances are low, the stored energy from the battery energy storage system is taking over the load basically, because obviously the intent is to utilize the fossil generation as less as we can, and then energy storage after the energy storage being used to discharge the. And this primarily like helps it out if you look into in terms of providing like the peak shaving. Peak shaving is again very important terms in the energy storage concept. Peak shaving means like when the load is at its peak, there are only two ways, right? Like because generation is fixed if we don't have energy storage. So either we have to curtail the load, we have to shut the load, or we have to find the way that how to take care of that load. So primarily these energy storage help it out at the peak duration when the energy storage or the battery energy storage type of systems are in the fully charged condition. A couple of very other important terms which we talk about like on the energy storage is capacity and energy. Capacity is primarily the megawatt and energy is the megawatt hour. Means very simple terms but very important terms, and plays a very important role at least for the battery energy storage system at the utility scale, because this defines that what is the backup duration this battery energy storage system can provide. And this is one of the most important, like I'll say, the technical attribute based on the application when someone is sizing and selecting the hybrid generation. Because again, as I say that if this is the utility scale, if this is the captive generation, if this is being used to take care to just avoid the transmission congestion, so applications are different, which drives it that how to select and size the best from the capacity and energy perspective. Resilience, again, means we talk about like, as a layman, if we say stiffness of the system, like in terms of any transient situations or in case of post-contingency situation after the fault, how the system behaves. Like I think we more or less aware about, at least from the technical background people, that combined cycle generation from their stability perspective are relatively considered as one of the most stable. But if you look into the stability of the like static sources of the inverters primarily which are being used for solar generation are not as stable as the combined cycle generations are. They are not able to primarily support, they are able to support nowadays about any of the voltage regulation for the grid. because whatever BESS are coming up, all the inverters are grid forming inverters. But all the solar inverters, more or less, I'll say in general, are the grid following inverter. When we say grid following or forming as a technical thing, I can say that they can't form the grid. They can't regulate the frequency. They'll just follow how the grid behaves. But BESS inverters are the grid forming, and they can just control the frequency. At least I'll say they can provide the virtual or synthetic inertia type of at times. Balancing and reserve means, I think we talked time and time that during the time of the day, during the long time, during the seasonal variations on the solar and wind, this provides some sort of balance and reserve to meet the generation demand. This I won't spend much time because we have already spent the good amount of time that what does power to power means, power to heat, power to gas. Means these are the different type of the energy storage technologies, and these energy storage technologies are being used in the different, like power to power, as I say that primarily like power is converting into hydrogen, and then hydrogen is being used as a fuel cell or to run the hydrogen based turbines. Power to heat is also like, as I was talking about nowadays, compressed energy storage system, which is storing energy in the form of thermal energy through the adiabatic process. Yeah, this is a couple of data which I just picked, which is very important. Like if we look into, as we are adding more and more solar generation, and if we know that it's not as easy to augment the transmission infrastructure per se, and at times what's happening that solar generations and wind generations type of thing depends upon the natural factor. Irradiance may be that even if the plant is installed of the 200 megawatt, that can generate to 190, 200 megawatt. And there would be the time when plant can generate 50 megawatt, or in the late evening hours, plant can generate anything. But when plant is able to generate 200 megawatt, whether the transmission infrastructure is adequate enough to take care of that particular generation. If not, what's the solution? Then obviously either to curtail the generation, means even if irradiance allows to generate 200 megawatt, but since the transmission infrastructure doesn't support, we can't wield the power of more than 100, 150 megawatt per se, because nowadays a lot of renewable infrastructures are coming up, at least in US, in India, at all the places of the world. If you look into western part of the India, we know that there are a lot of challenges like the big solar parks which are coming up, the transmission infrastructure. So if we look into three data, I'm not talking about India obviously, but if you look into countries like who are advanced in renewable, in Germany, renewable curtailment cost is around 3 billion euro in 2023 only on account of the transmission line constraint. They had to curtail it. This means that solar capacity based on the solar irradiance available could generate, but they couldn't generate it because they were not having the transmission infrastructure to just export the power. In UK, if we look into curtailment, was around 1.5 billion pounds from 2021 to 2023. Even if you look into country like Chile, which is too good from the wind generation perspective as well, around 10% of the renewable generation was curtailed. And if you look into in terms of the energy number, this is 2.38 tetrawatt hours. This is again one of the things which I very briefly touched about the duration. Means what does it mean? That as we are moving it to just reduce the emissions, to add more and more renewable generation, again as we say more and more renewable, we are mainly talking about solar, wind. Obviously, like people are now talking in the big way, at least in US and Germany, about nuclear, small reactors, SMRs type of. But if we talk about solar and wind, without doubt, we need to increase the duration of the energy storage. Because very important, like as we go for from 30% to the 80% of the renewable generation, without doubt, we have to increase the energy duration to meet the gaps when the generation is not available. So this is one of the things, like as we are looking into, there is a time when we have to add around 10 hours and then 100 hours of the backup energy duration. This is, we have more or less already talked about. This we talked about when I was talking about energy arbitrage and peak shaving type of things, so won't cover much on that. This is frequency regulation type of thing which touched base. Just to conclude it, if you ask to me, this is again one of the very important thing which covers primarily, if you look into, the x-axis talk about the long discharge and the y-axis talk about frequent use. When I say long discharge, this means that we need long discharge means the longer duration of the storage, and we want that we have to use it quite frequently. Then obviously there are the different applications like about the capacity, about the load following, energy time shift. Similarly, if we talk about the short discharge and occasional use, this is primarily to support the service power quality per se, to regulate it type of. So these are the different applications where energy storage is being used. So quite important to decide that what type of energy storage, what should be the capacity, and what should be the backup duration or the storage duration for that energy storage system is all depends upon the application where these are being used. Thank you.